Good morning, honors chemistry students. Today, I would like to examine the molecular geometry of the carbon dioxide molecule. And as always, we're going to start with the chemical formula. The chemical formula of CO2 is just that, CO2. This is one of those molecules that has more than two atoms. So therefore, it's important to determine which of the atoms is the central atom. And one strategy for that, in determining molecular geometry, is to look at the number of valence electrons that each atom has individually. Carbon has 4 unpaired valence electrons, so we say that it has a valence of 4. And oxygen has 6 valence electrons since it's a member of group 6, but 2 of those are unpaired, so we say it has a valence of 2. Whichever atom has the greater number of unpaired valence electrons is going to be designated the central atom. So in this case, carbon is going to be our central atom because it has a greater number of unpaired valence electrons. As always, I want you to include a column called illustration, which really is the last thing you do once you've completed the paperwork. Once you've modeled your molecule, then you complete the illustration. So we're going to kind of move over to the AELD, or the atomic energy level diagram. And in doing the atomic energy level diagram, we're going to position carbon as the central atom. And at issue here is carbon has an atomic number of 6, so it has 6 protons and 6 neutrons. And it has 6 valence electrons that we need to place to go on the first energy level and the 1s sublevel, and then we're going to place 4 on the next energy level. We know that carbon forms 4 bonds, and in fact, carbon was used to develop hybridization theory. And we're going to view carbon as having 1 electron in the s, and then 1 in each of the p's. Theory says, if you followed the pattern that we have heretofore established, that carbon would have 2 2s electrons and 1 in each of the 2 p's, but we know carbon forms 4 bonds. So it's theorized that an s gets promoted to a p to create 4 unpaired valence electrons. And to those unpaired valence electrons, we're going to establish bonds with each of 2 oxygen molecules that have 8 protons and 8 neutrons. Thus, we have to account for the placement of 8 electrons. So we're going to say the first 2 electrons in this oxygen are at the 1s, and because oxygen's in group 6, we have to account for the placement of 6 electrons, 2 of which are going to be in the 2s. We're going to put 1 in this 2p. We're going to represent 1 in that 2p being shared with carbon, another one here, and the 6th one there. So there is our AELD for oxygen. Let's go ahead and bond the next oxygen, which also will have 8 protons and 8 neutrons and 8 electrons. We'll start by placing 2 electrons in the 1s, and then we'll place 6 valence electrons, 2 in the 2s, 1 in this 2p, 1 in that 2p, bonding with carbon, 1 down below, and we'll create that second lone pair on top. So you can clearly see that each oxygen has 6 valence electrons, 2, 4, 5, 6, 2, 4, 5, 6, and carbon has 4, 1, 2, 3, 4. So as this AELD is currently drawn, you can clearly see that none of the atoms are in the octet state. In other words, according to carbon's perspective, according to oxygen's perspective, it has 7 valence electrons, 2, 4, 6, 7. This oxygen has 7, 2, 4, 6, 7, and carbon right now has 2, 4, 5, 6. So how do we remedy that? Theory says that we're going to remedy that by forming a second shared pair of electrons. So we're going to move this electron and this electron to represent them as a shared pair right there. And in doing so, we've just formed a double covalent bond. Remember that each covalent bond involves 2 electrons. Since we have 2 shared pairs, we actually have 4 valence electrons in bonding. And then on the other side, the same approach is going to be taken. We're going to relocate this p electron and that p electron. And we're going to create 2 shared pairs of electrons here. And we'll try to complete these orbitals here and here and there. So now we have a molecule which has, in fact, 3 atoms, each of which are in the octet state. So in other words, if we wanted to cover up any one of those atoms, we should be able to demonstrate that each is in the octet state. So you can clearly see that this oxygen has 2, 4, 6, 8 electrons, valence electrons, as does this oxygen now, right? It has 2, 4, 6, 8. And carbon also has 8 valence electrons, 2, 4, 6, 8. So each of those atoms is now considered to be in the octet state. The next diagram we're going to prepare for you is the orbital notation diagram. It's a pretty interesting diagram for CO2 because you have to represent the shared pairs of electrons in each of the orbitals. I might suggest that you start with carbon, and I'm just going to ask that you draw the 2s and the 2p. According to how we have drawn it here, well, let's do this. Carbon has 2 electrons in the 2s and 1 in each of the 2p's, but given that it's a nonmetal, that arrangement would predict that it only forms 2 bonds, and we know that's not true. So according to hybridization theory, it's theorized that this valence electron is actually promoted to a p, which explains why carbon can form 4 bonds, because theory says that it has 4 unpaired valence electrons. And that being said, we now have to go about the task of representing how carbon shares its valence electrons with oxygen. Oxygen also has its valence electrons on the second energy level. It's got 2 in the 2s. Then it's got, we'll draw these going down, 1 in this 2p, 1 in that 2p, 1 in this 2p, and 1 going up. So you can clearly see that we can represent a shared electron pair here between carbon's 2s electron and oxygen's 2p, and then also represent 2p orbitals, or the electrons in 2p orbitals being overlapped. So that's 1 oxygen. And then on the other hand, we could represent the next bond forming with oxygen by showing how those valence electrons of the remaining oxygen are paired. So we'd go up, down, then we'd go down, 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 up. We're sort of drawing this backwards so we can get to 4 shared pairs of electrons. And there you go. There is carbon's 4 shared pairs of electrons. Kind of interesting arrangement. The next diagram that I'd like for you to represent is the electron dot. And again, you're going to clearly see the need for establishing 2 valence electrons, 2 individual double covalent bonds, which each have a shared pair of electrons. So we've got carbon, once again, if you think about it, originally it had 4 unpaired valence electrons. Then you had an oxygen here, right? With its 6 valence electrons, 2 of which are unpaired. That's 2, 3, 4, 5, 6, correct? And then we've got another oxygen over here. There's 1, let's do it this way. There's the 2s, a 2p, a 2p there, a 2p there, and we'll go back and share that one. But you can clearly see we get into this situation where there is, none of the atoms are in the octet state. So what we're gonna do is, just like we did with the 8ELD, we're gonna kind of shift positions of things, of some of the electrons here, and we're gonna form a second shared pair here, and then we're gonna form a second shared pair here. So now, if you look at this from the perspective of each individual atom, oxygen now has 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8, and carbon has 2, 4, 6, 8. So all the atoms are in the octet state. The next representation that I want you to represent is the structural formula, which simply represents the shared pairs of electrons between the atoms with lines to represent the bonds, okay? So once again, carbon has 2 bonds with each oxygen. And remember, in the structural formula, we don't represent non-bonding or lone pairs of electrons. So we're gonna come back to look at the electrons in the system here. So to predict the number of bonds that form, we want to look at how many electrons are in this entire system. I think the easiest way to do that is to use the electron dot. Each oxygen has 6. 6 and 6 is 12, and carbon has 4. So 12 and 4 is 16. And we want to compare that to how many electrons are actually needed for each of the atoms to be stable. Well, each of the atoms needs to be in the octet state, so 8 times 3 is in fact 24. So we have 16 electrons, but the system needs to make it look like it has 24. So the way it's going to do that is to form 3 shared pairs of electrons. So we're going to look at the difference between 24 and 16 and divide that by 2 electrons per bond. The difference between 24 and 16 is 8. 8 divided by 2 is 4. So we predict the fact that we're going to have to form 4 bonds, which in fact you see that we did, right? Because there's 1, 2, 3, 4 covalent bonds. And the numerator in this quotient, beautiful. The numerator in this quotient, 8, represents the number of electrons involved in bonding, and you can clearly see that we've got 2, 4, 6, 8 electrons involved in bonding. So therefore, we predict that there will be a total number of 4 bonds. And the next representation that I would like you to draw is the Lewis dot structure. And the Lewis dot structure really is a hybrid of the electron dot and the structural formula, in that you represent shared pairs of electrons with lines, and you represent lone pairs with appropriate symbols. So we can see that each oxygen has a double covalent bond along with 2 lone pairs of electrons. Keep in mind that the bonding electron domains are referred to as just that, bonding domains, and the lone pairs are referred to as non-bonding domains. The next thing that I would like to look at is bond type. Bond type's important because it examines the all too important electronegativity differences between two atoms that are bonding to determine whether or not the bond that is formed is polar. So the electronegativity of oxygen is 3.50 and the electronegativity of carbon is 2.55. That difference turns out to be 0.95. That difference gives you a window into the extent to which carbon and oxygen share those pairs of electrons. And keep in mind that if the electronegativity difference is between 0.0 and 0.4, we identify a bond as being nonpolar covalent, or NPC. If the electronegativity difference is between 0.5 and 1.7, we say a bond is polar covalent. And if it's between 1.8 or greater, we say that a bond is ionic. 0.95 pretty much is in the middle of that polar covalent range, so we'll refer to this as being polar covalent. The end result of that is there's a separation of charge, and the charge is assigned to each of the three atoms. Given that oxygen is more electronegative than carbon, we assign partial negative charges to oxygen and partial positive charges to carbon, which I would like you to go back and pay homage to on each representation that we have established. So the bonds between carbon and oxygen are in fact polar. The question remains, though, whether CO2 is actually a polar molecule. There's some debate about that, but we're going to kind of stick to straightforward theory to answer that question. In a moment, the next calculation that you have to do is to examine total pairs of electrons, which includes bonding pairs plus lone pairs. It's interesting that since we have a central atom, carbon, we can say that for carbon, right here, for carbon, yes, it has two double covalent bonds, but keep in mind that double bonds count one bonded pair. So we say that carbon has one bonded pair and 0 lone pairs for one total pair of electrons or electron domains. We could also do that calculation for oxygen. Oxygen, let's back up here, a little mistake time. Carbon actually has two multiple bonds, so this should be a 2 and this should be a 2. That's a save. Oxygen, on the other hand, has a double bond with carbon. That counts one bonding pair because multiple bonds count 1. Oxygen has two lone pairs, so 1 and 2 is 3. So that has important implications for predicting how the electrons are going to arrange themselves around not only the central atom, but around the oxygens as well. So in consideration of valence shell electron pair repulsion theory, we're going to go ahead and predict that two total pairs of electrons around carbon predicts a linear arrangement of those electron pairs. And 3 total pairs around each oxygen predicts a a trigonal planar arrangement. So we're going to go ahead and establish those bond angles like so. Keep in mind that the bond angle between the carbons and oxygens is going to be 180 degrees. And so overall, we would say that that's linear. And the bond angle between oxygen's lone pairs is going to be 120 degrees. So we say or predict that the arrangement of electron pairs around the central atom is going to be linear And the arrangement of electron pairs around the oxygen is going to be trigonal planar. But keep in mind that when we calculate or examine the overall geometry, we're not looking at lone pairs, we're only looking at bonded pairs. So the companion theory to Vesper theory is called hybridization theory. So let's go ahead and work on this for just a little bit. So, to explain the arrangement of electrons around carbon, it can be said that carbon has an s and 3 p's on the second energy level. And theory says that to explain the arrangement of 2 total pairs of electrons, an s overlaps with a p to create sp hybridization. So we have 2 degenerate equivalent sp hybridized orbitals are predicted around a central carbon atom. So we're going to go ahead and draw that here, where we have those 2 hybridized orbitals arranged, by the way, in a linear arrangement, because 2 pairs predicts a linear arrangement. On the other hand, oxygen has 3 total pairs of electrons. So the arrangement of its electron pairs is going to be predicted to be trigonal planar. So you're going to draw your hybridized orbitals, because 3 total pairs predicts what we call sp2 hybridization. And we'll kind of fill in those details in a moment, but we've got another oxygen over here, and then we've got one here. Yeah, these are supposed to be overlapping, right? So for carbon, we're going to have 1 direct overlap of electron pairs here and there. Each oxygen is going to have 2 lone pairs, illustrated here. So overall, right now, we've accounted for 5 electrons from oxygen, each oxygen, and 2 from carbon. So the deal is this, that in sp hybridization, you may note that 2 orbitals are unhybridized. If you think of the sp hybridized orbital as being along the x-axis, there should be an unhybridized orbital vertically along the y, and then also another unhybridized along the z, because the bonds on either side are referred to as sigma bonds, and sigma bonds have a 180-degree bond angle. So therefore, single bonds are always sigma bonds, double bonds are always pi bonds. So we're going to have 1 sigma bond here at least. The question is, how do we account for the remaining pi bonds? And keep in mind also that the bond angle between these electron pairs is 120 degrees, and we say that the hybridization that results is sp2 hybridization, whereas with carbon, we say it's sp hybridized. Sp hybridization predicts a 180-degree bond angle, sp2 predicts 120. And you may note, if oxygen has sp2 hybridization, that means an s overlaps with 2 p's, but that leaves us 1 unhybridized orbital remaining, and we're going to put that unhybridized orbital here, and here, and here, and here. Capiche? So we're going to place 1 of carbon's remaining 2 valence electrons there, and a valence electron for oxygen there, and we're going to form an indirect overlap here, which is referred to as a pi bond. Remember, Single bonds are sigma bonds, and multiple bonds are pi bonds. So we can also place a valence electron here for oxygen and carbon's lone remaining valence electron there. You could really put it just about anywhere, but what we want to do is create another shared pair of electrons. So you can clearly see that the first bond is a direct overlap and is referred to as a sigma bond. The indirect overlaps are pi bonds. So the arrangement of electron pairs around carbon predicts carbon to be a linear molecule with a bond angle of 180 degrees because it's sp hybridized. That's the take-home point. Now, when we get to the actual geometry, we cover up lone pairs and only look at bonded pairs. So we're going to represent this in this way, almost like it looks like a Lewis structure, right? So that we have the lone pairs of oxygen kind of represented in a tight sort of way around the oxygen. And you can see that if you can draw a straight line through this molecule. So we're going to say the actual geometry of CO2 is linear and the bond angle is 180 degrees. Whew! And then we get down to bond energy. You can look this up. Bond energy values are generally recorded in kilojoules per mole. And in doing so, since these are double bonds between the carbon and oxygen, the carbon and oxygen bonds are going to have a bond energy of 1072 kilojoules per mole. That's large because carbon has two shared pairs. So each double bond between carbon and oxygen has that bond energy. That's the energy that must be released when the bond is formed, or the energy that must be supplied to break the bond. In terms of bond length, as we discussed in class, bond length is typically provided in picometers. The bond length is 123 picometers, which is shorter than the carbon-carbon single bonds, because as you add bonds between carbons, or between carbon and oxygen, the carbon-oxygen single bond is much longer than the carbon-oxygen double bond. And then we get to the AXE system. In the AXE system, we're only looking at the central atom. And we can say that carbon is the central atom and it has two bonded pairs. So we say that this is an AX2 molecule. And in terms of polarity, this is the take-home point. Carbon has two polar bonds, but the issue is the polar bonds are oriented in such a fashion that the direction of electron pull is equal and opposite. And by the way, in these future diagrams, I needed to represent the charges on each of these, right? The oxygens are negative, the carbon is positive. We should try to do that here. The carbon's positive, the oxygens are slightly negative. Same thing here, the oxygens are slightly negative. The carbon is slightly positive. We refer to this direction of electron pull as being symmetric. So I want to say this direction of electron pull is equal and opposite, and the key word that I would attached to that is symmetric. It has a symmetric electron pull, which gives it a zero dipole moment. So since the direction of electron pull is symmetric and the charges coincide with each other, we would say overall this molecule is non-polar. Although there are those that argue that it's weakly polar, which explains why CO2 combines with water to form carbonic acid, which has profound implications for climate change theory in the environment. And that is CO2. The next molecule that we will take a look at is water.